Welcome, everyone. It's great to have Marco Pavone with us. Marco is an associate professor in the Department of Aeroastro at Stanford. He directs the Autonomous Systems Lab, where with his group, he works on analysis, design, and control of autonomous systems in many application domains, self-driving cars, in aerospace vehicles, multi-agent systems. He's currently in partial leave from Stanford and recently joined NVIDIA, where he directs the autonomous vehicle research, building a group at the intersection of autonomous systems and very large data sets somehow. Before joining Stanford, Marco was a research technologist in robotics at NASA's Jet Propulsion Lab. And before that, and absolutely most importantly, he got his PhD from MIT. Was in, yes, clap, please.
Indeed, so.
It was in 2010?
2010, yes.
There you go. Marco has received all sorts of awards, from the highly exclusive and prestigious Presidential Early Career Award from the hands of President Obama, I think, to the more in awards, like being recognized as one of America's 20 most highly promising investigators under 40. I don't know if that still applies.
Unfortunately not. Just a little bit.
So Marco, welcome back to MIT.
Thank you very much.
Thanks for taking the time to come visit us.
Of course, my pleasure. Of course, every time I come back to MIT, brings me back some memories of the great time I had here. I did my PhD in Leeds on the 7th floor, and I really had a great time. Well, thank you very much for the introduction, and thank you very much for having me. So today what I'm going to do is to give you an overview of the work from my research groups at Stanford and NVIDIA toward addressing key open problems in the field of vehicle autonomy, and in particular in pursuit of safe data-driven autonomy. So now, my research broadly is in the field of decision-making and planning for autonomous systems. And the key application domain is represented by space robotics. Specifically, as a research technologist at NASA JPL before joining Stanford, I worked on the entry, descent, and landing of rovers on the surface of Mars. And currently, through a collaboration with NASA Ames and the group of Mark Kutkowski at Stanford, we're working on designing, planning, and control algorithms to grasp and manipulate objects in space. Here, I'm showing a short video of some recent experiments we carried out on the International Space Station, where we tested a gecko-inspired gripper mounted on a free-flying robot, which in this case was attaching itself to the walls of the International Space Station and is meant to help astronauts with a range of activities on the space station. I love involving students in my space-related research. To this purpose, I founded at Stanford the Stanford Student Space Initiative, which is a student club that now involves more than 200 students doing projects in a variety of fields, from high-altitude balloons to rockets to satellites, astrobiology, and so on. The group has achieved a number of world records, for example, in terms of flight endurance for latex-based balloons. And it has even spun off some startups, such as Windborne, which is a high-altitude balloon startup. But my other key application domain, and indeed the focus of my presentation today, is represented by ground autonomous vehicles, and in particular, self-driving cars. And my overarching goal in this field is to develop the next generation of AV stacks by making them increasingly data-driven. In particular, the three research thrusts of my work are, first, developing robust and human-centered autonomy algorithms, which can robustly reason about complex interactions with other humans on the road for the purposes of both real-time control as well as simulation. Second, developing methods to provide both offline and online safety assurances for the different components of an AV stack, and in particular, those components that are based on machine learning techniques. And third, developing data-driven yet modular autonomy stacks, which combine the flexibility of modular architectures with the efficiency of end-to-end data-driven architectures. Of course, some of this research is applicable also to the domain of space robotics, but with some important exceptions. For example, in the case of self-driving cars, we need to reason carefully about the interaction with the other humans in the environment. This is not something that you have to do in the context of space robotics applications. Now, in the remainder of this talk, I'll provide more details about my current and planned work in each of these areas, starting with the topic of human-centered and robust autonomy. And in particular, safely and efficiently dealing with human agents on the road is indeed one of the key challenges in the field of vehicle autonomy, ground vehicle autonomy in particular. This video shows, for example, the very complex and sometimes aggressive interactions that arise when driving in my home country in Italy. This is taken from Naples. Importantly, this video showcases how interactions on the road are really an exercise in negotiation. An autonomous vehicle should be able to perform such negotiations for safe and efficient driving. In other words, autonomous vehicles should be able to perform what I refer to as a human-centered interaction-aware decision-making, which refers to the capability of first proactively interacting with other human agents to infer their intents, while concurrently using this information to take actions that account for possible responses. And to make things even more complicated, interaction-aware decision-making needs to be robust to several sources of uncertainties, for example, stemming from the perception module. There was something particularly weird interaction there. OK, so a key first step to enable interaction-aware decision-making is to develop models for intent prediction and trajectory forecasting, basically predicting what other human agents in the scene are going to do in the future. And here by future, I mean the next 3, 5, maybe 10 seconds. In our work, we have embraced a phenomenological approach, whereby we learn relative likelihoods of human actions and responses without making any structural assumptions on how humans do their own reasoning. And this is in contrast to ontological or theory of mind approaches, such as, for example, inverse reinforcement learning, which postulates some structure on the human decision-making process, for example, in terms of a cost function that we postulate a human is trying to optimize. But the problem with the theory of mind approach is that this postulated structure is sometimes difficult to reconcile with how humans actually drive. Now, a particular class of phenomenological models is represented by generative models, whereby we want to learn a distribution P about future human actions, denoted as U sub H T plus 1, conditional on the interaction history, denoted by X and U, and highlighted in gray, as well as condition on a robot candidate action, U sub R T plus 1, and highlighted in purple. The interaction history represents, for example, the history of relative poses between the AV systems we are controlling and another human, for example, human-driven vehicle. Here, T is the current time, thus T plus 1 is the next time step. Now, conditioning on history lets you infer things about human behavior, such as alertness or aggressiveness, while conditioning on the autonomous car's future, so candidate future robot action, allows us to capture the interactive aspect of an interaction. So basically, we want to learn a distribution of human actions and next time step, conditional on what has happened in the past and what the robot might do in the future. So that then, if you have a set of motion primitives, we can select the one that, according to some cost, optimizes end-to-end performance. Now, over the years, we have developed a fairly general generative model to forecast human trajectories, which we refer to as a trajectron plus. This framework is based on a conditional variational autoencoder model and can ingest as conditioning variables for the predictions a vast set of heterogeneous data. From dynamical information, clearly a pedestrian moves in a way that is different from the way that a biker or a car move, and you want to use that information to make your prediction precise, all the way to maps encoding information such as boundaries and crosswalks, and even human silhouettes, for example, to predict pedestrian movement. And some elements of Trajectron++ has now been transferred to the NVIDIA AV stack and are part of the NVIDIA AV product. We have thoroughly tested the Trajectron++ in closed loop with the planning algorithms on a test vehicle at the Center for Automotive Research at Stanford, which I co-direct. And the role of the human-driven vehicle is taken by a small RC car that you can see here, which is remotely controlled by a student. And the autonomous car is this car here that is completely autonomous. And this is the small RC car is the analog to a human-driven vehicle. The reason why we use an RC car is that here we are stress testing the algorithms in highly interactive scenarios. So we're asking the student to behave in unreasonable ways, if you will. For example, this is a traffic weaving scenario. And we ask the student to, at some point, immediately swerve into the trajectory of the autonomous car and see how the autonomous car reacts when you have behaviors that are really at the limits of what the trajectory forecasting algorithms can predict. Now, leveraging Trajectron++ as our base trajectory forecasting model, we're currently working on 4 main themes that, in my mind, are key to fully enable interaction-aware decision-making. First, building a transferable models of human behavior which can be readily transferred to different areas of the work. So if you take a model that has been trained with data from San Francisco and you try to use it to forecast people in Italy, it wouldn't work. And every time you go into a new city, you have to retrain your model from scratch. The business doesn't scale. So here you want to build models that can adapt very quickly to new environments, new areas, with just a few additional samples. Second, we're working on making these models robust to errors and uncertainties stemming from upstream perception sources. Third, we are developing simulators that can leverage such models to simulate realistic human motion in closed loop with a simulated autonomous vehicle. Simulation is probably the holy grail in the field of autonomous vehicles, but there's still a key gap in terms of how we can model human agents. And this gap does not really allow us to fully use simulation, for example, for the purposes of closed-loop verification and validation. And finally, we're working on devising algorithms that tightly couple prediction with planning. So in the interest of time, I will only provide some details on how to make such prediction models robust to input uncertainty. Specifically, no matter how sophisticated the trajectory forecasting and decision-making algorithms are, they still might fail to produce safe and efficient behaviors if they're fed with erroneous information, for example, from onboard perception. And indeed, one of the main challenges that arises when designing autonomy stacks is managing uncertainty between components, specifically because this uncertainty cascades and propagates downstream in your decision-making stack and in your AV stack. Toward this end, we have been investigating the incorporation of numerous sources of uncertainty throughout the autonomy stack. For example, accounting for object detection and classification uncertainty in prediction, as well as leveraging prediction multimodality for the purposes of planning and control. And the ultimate goal here is to enhance end-to-end robustness through careful accounting and calibration of all uncertainty sources. As an example, one of our latest results focuses on making methods for predicting the actions of other agents more robust to object tracking errors, and in particular, fragmentation and identity switching. And in this video, we can see these types of tracking errors in the wild. Every time the video pauses, there is a red circle around the tracking error and the type of error above it. And the parked cars on the left frequently experience identity switches, which is where the identities of two objects are switched, usually due to similar appearances or proximity to each other. Now that the vehicle is turning left, we see examples of fragmentation, where an object tracking is broken into fragments. And this is typically due to occlusions. Now, the problem is that such tracking errors significantly affect many state-of-the-art prediction methods. For example, in the top left image, we see reasonable predictions of motion to the left, represented by yellow lines, and emanating from the yellow bounding box of a car. On the right, a spurious detection near the car causes an identity switch, which makes the same car, now marked in purple, to have unrealistic off-screen predictions. And you can imagine how these erratic predictions would be problematic from the point of view of decision making. And the reason why we have this erratic prediction is that the switch, the identity switch, is mistakenly interpreted as a sudden lateral motion, which in turn fools the prediction algorithm. To quantitatively measure the effect of tracking errors in prediction, we evaluated the performance of state-of-the-art prediction algorithms on 2 real-world driving datasets. And in both, we compare prediction performance on agents with perfect, that is, human annotated tracking, versus tracking computed via the dataset's best performing tracker. And overall, we found that prediction methods experience a significant increase in their error rates, up to 30x, in the presence of tracking errors. So this is problematic. Now, to remedy this, we took a step back and asked if tracking objects is even necessary for prediction. Specifically, the idea is that instead of using the usual hard data association from tracking to obtain past trajectory data, our key insight is to directly use previous detections and their similarity between frames, referred to as affinity, to make the predictions. In other words, we remove the hard data association step that is used to produce tracklets, and which can be interpreted as an information bottleneck, and instead directly use detections along with their affinity between frames as prediction inputs. So it's a relatively simple idea, and here the idea is really to remove an information bottleneck, and we'll come back to this idea later. And when evaluating predictions on objects with tracking errors, our affinity-based prediction method achieves almost 80% reduction in prediction error, which is a dramatic improvement. So the takeaway message is that systematic accounting of trajectory propagation throughout the Vstack provides great opportunities toward bolstering system-wide robustness, in addition, of course, to improvements with respect to the individual task-specific algorithmic components. And we're currently working on a number of topics related to the theme of system-wide robustness. First, the approach that I just discussed, as I mentioned, essentially exploits the rather intuitive idea of removing informational bottlenecks, such as hard data associations, which might remove crucial information that might be useful in subsequent stacks, modules in the Vstack. And we're currently working on systematically scaling up this idea throughout the Vstack. Second, we're working on statistical approaches to calibrate the uncertainties produced by the different modules, in particular to support decision-making and planning. And finally, we're working on developing datasets, for example, for prediction research, which explicitly provide uncertainty information in order to foster more research on the broad topic of robust autonomy. OK, well, now machine learning obviously is ubiquitous in modern autonomy stacks. And enables a wide range of capabilities from prediction to perception, as we have just discussed. However, providing safety assurances for such models represent a major challenge due in part to their non-deterministic runtime behavior. So a key thrust on my work, since my work is focused on safety-critical systems, is to devise techniques to endow autonomy stacks with safety assurances. Not safety guarantees. I'm not a believer that we can really achieve guarantees, but at least assurances that these systems are going to behave well at runtime. And in particular, we're working on a number of related problems. The first one is to develop techniques to robustly train machine learning models, and at the same time devise safety KPIs that allow us to measure the safety of learning-based components at scale. And we're using some of these safety KPIs, for example, to measure the safety of the perception networks in the NVIDIA stack. Second, we are developing tools to monitor learning-based components online, that is at runtime, in order to detect and possibly identify possible anomalies in the stack. And this work partially in collaboration with Navid Azizan here at MIT. And third, we are devising algorithmic modules referred to as safety filters, whose goal is to bound online the behavior of learning-based components in order to enforce safety by design. For example, NVIDIA uses a safety filter as part of its decision-making architecture, and the safety filter is referred to as the safety force field. And I really believe that such a multi-pronged strategy is needed in order to achieve the level of trust that is required to deploy these systems at scale. In the interest of time, I will only go into the details about my work on runtime monitoring. And here the idea is that no matter how well a machine learning model is trained and optimized, it can still perform poorly, as it might encounter situations that are very different from those seen in the training data. And concretely, consider the setting where an autonomous aircraft is tasked with tracking the center line of a runway. And we assume that we have a perception deep neural network, which translates the high-dimensional visual observations, such as the image of the runway on the left, to an estimate of the state of the system. In this case, lateral displacement with respect to the center line of the runway. And then this displacement information is used by a controller to produce an action to take in order to track the center line. So fairly simple task, which is mostly a toy example, but has many of the aspects that are needed in order to stress test the ideas of runtime monitoring. Now, the deep neural network is trained on labeled examples of observation state pairs, which are drawn from some joint distribution. The joint distribution is clearly a function of the environment, and importantly, is a function of unobserved context variables, such as weather conditions, lighting conditions, and so on and so forth. Now, when the context and environment changes, for example, we are operating at night, as seen in the left side of this image, the observations may be quite different from those seen during training. That is, we have auto-distribution observations. And the difference can lead to faults in perception. For example, a faulty estimate of the lateral displacement error, which in turn will negatively impact the closed-loop performance of the system. So to enable safe, trusted deployment of these learned systems, it's critical we can detect and isolate these faults at runtime, online. And with this goal in mind, the question is, how can we equip pre-trained deep neural network models with monitors that can provide an anomaly signal warning us about auto-distribution events during operation? So to address this question, first one has to be rigorous about what we mean by out-of-distribution detection. And perhaps the most intuitive definition of auto-distribution is in terms of distances in the input space. An input, such an image, is deemed auto-distribution if it is far enough from the input seen at training time. While this definition is intuitive, probably is the most intuitive you can come up with, it does present a number of challenges. First of all, it's hard to define a meaningful, tractable notion of distance on hard-to-define manifolds, such as the space of images. But practically, this approach requires storing training data at test time to carry out these comparisons, which may be prohibitive from a memory storage standpoint and ultimately doesn't really scale. So a reasonable alternative entails learning a parametric model of the training distribution, leveraging advances in generative modeling. However, these approaches are typically not suited for evaluating correlated sequences of inputs, such as those produced by deep neural network in an autonomous stack. But most importantly, these approaches are inherently disconnected from the prediction task. We're just defining here things with respect to the input space, neglecting completely what happens in the output space. But in reality, we are more interested in understanding how changes in input would change the model's predictions, because this is ultimately what we care about from the point of view of closed-loop control. So to address the key shortcomings, our insight is to embrace a notion of auto-distribution detection from the perspective of functional uncertainty. Specifically, we argue that an input is auto-distribution for a given prediction task if the prediction for that input is not well determined by the training data. This is appealing because it focuses on inputs that are different in a manner that could affect the underlying model predictions. But how do we quantify this type of uncertainty? So to do so, we turn to Bayesian methods. So the typical approach in Bayesian methods requires three main steps. First, we define a prior over functions that map input to outputs. So this figure on the right visualizes sample from such a prior of functions, mapping a scalar input to a scalar output. Next, given the training data, we need to compute the posterior distribution over functions that are consistent with the training data, here denoted by the gray dots. So the gray dots in this figure are the training data, with respect to which we compute a posterior with respect to the functions that might fit this data. And to do so, we leverage Bayes' rule. And finally, given these posterior over functions, we can measure the remaining uncertainty over the output and new test inputs to classify inputs as in or out of distribution. For example, for inputs in this area, we have agreement with respect to all our models. So we said that these are inputs in distribution. Here we have a lot of uncertainty in terms of the predictions of our model. So we deem those inputs as out of distribution. That seems reasonable. And translated to our context, this recipe entails first identifying a prior over the space of functions, mapping the potentially very high-dimensional input space of a deep neural network into the output for a given prediction task. Second, devising methods to efficiently compute and representing the posterior over such a function class. And finally, finding a way to compute the predictive uncertainty with low latency in order to distinguish between in and out of distribution samples, and in case raise an anomaly signal. The question is, how do we then implement these three steps in the context of large-scale deep neural network models? So our approach, and again, this is work in collaboration with NVIDIA Zizan here, is called Scod, which stands for sketching curvature for out-of-distribution detection. Scod is a model-agnostic approach for equipping any pre-trained deep neural network model with a measure of epistemic uncertainty. In particular, Scod applies the Bayesian methodology that I just discussed by first constructing a prior over functions by linearizing the trained neural network with respect to the weights, and then imposing a Gaussian prior on the deviation from the linearization point. So this is the prior functions that we use as a first step in our Bayesian methodology. This prior describes a wide range of nonlinear functions that map from the input space to the output space of the deep neural network, and by construction includes functions that fit well the training data. If we just set the delta W, so the displacement in the weights to 0, we recover the model that fit the data we trained it with. Why do we use a linearized model? Well, with this linearized model, we can achieve analytic posterior inference, which would not be possible with a nonlinear model. Specifically, the posterior over the weights for this linearized model is a Gaussian whose covariance is a function of a Hessian of the training loss with respect to the weights. And there is no particular magic here. It's basically relatively standard Gaussian transformation computation. But the point, and this is really the crux of the problem, is that even for modestly sized networks, representing this high-dimensional covariance matrix can still be intractable. And the key insight we leverage here is that for over-parameterized deep neural network models, this Hessian exhibits very rapid spectral decays. And thus we can achieve substantial computational gains by approximating this covariance matrix with low-rank factors. And in particular, we use a sketching-based technique to estimate the posterior covariance in terms of low-rank factors. The spectral decay is extremely fast. Typically, we only need 50, 60 modes. So at test time, we can obtain low latency uncertainty prediction by analytically propagating the posterior Gaussian on the weights to the output of our linearized model given a new input. And again, here there is nothing particularly special. It's just a transformation of Gaussians. And finally, we can compute a scalar measure of uncertainty at runtime by evaluating the entropy of this predicted distribution, which can then be thresholded to decide whether a given test input is in or out of distribution. So the methodology has a number of moving parts, but the key ideas are first to use as a prior function a linearized version of the neural networks with respect to the weights, and we attach a Gaussian priors with respect to the linearization variables. And everything else then is simply a relatively straightforward Gaussian transformation, but we have a bottleneck, which is the fact that it's difficult to represent the covariance matrix for such large-scale models. And here, as an insight, we use the fact that these matrices actually have very rapid spectral decay, so we can effectively approximate them with low-rank factors. Once we do that, we can then map the Gaussian posterior over the weights into predicted uncertainty for a given test input. And then once we have this predicted uncertainty distribution, we can measure how much uncertainty we have in different ways. One possible way is to compute the entropy of the distribution, and then we get a number. We thresholded it, and then we decide whether we are in or out of distribution. Let me show the application of this approach to the autonomous aircraft taxiing example, as I mentioned before. Remember, the one important thing of this method is that it has to be fast. Typical inference times for deep neural networks, the budget for it is 5 milliseconds and below. And you are building a monitor on top of it. So, of course, you want the overhead of the monitor to be much less than what is required for the inference for these DNNs. So typically, you're really operating in a millisecond sub-regime. Now, the input of the perception neural network is represented by images from a wing-mounted camera. And as I mentioned before, the output is the lateral displacement of the aircraft with respect to the center line. In the simulation I'm about to show, we first test the runtime monitor on images similar to those seen during training time, that is in clear morning conditions. And on the right-hand side, I will plot the output of the runtime monitor as a function of time. I will also mark any time that the network makes a significant estimation error with an X. So we see here that, let's see if we can, oops. Yeah, so we see here that when applied to clear morning conditions, the output on the monitor is low, and everything is deemed as nominal. But as we start moving to afternoon condition, we start seeing shadows. And this is something that was not included in the training data. And the output of the monitor went up. And so these examples were deemed as out of distribution. And these are examples that caused estimation errors, basically providing an erroneous estimation of how far the airplane was from the center line of the runway. Now, so you might ask, why didn't you include the shadows and afternoon images in your training data set? Of course you would. The point here is that no matter how carefully you curate your training data set. There are always going to be things that you did not anticipate. And this runtime monitor seems to be quite capable of capturing those conditions. So at least we know that something bad is happening. Then the question is, what do you do with it? So this was qualitative. To study the performance of Scod more quantitatively, we measure performance of how well we can classify OOD inputs from in-distribution data for a variety of data sets. And we consider a classifier that operates by applying a threshold on the uncertainty signal. The choice of a threshold, the choice of this threshold induces a trade-off between the fraction of OD data that is correctly flagged as auto-distribution, so the true positive rate, and the fraction of in-distribution data that is incorrectly flagged as auto-distribution, the false positive rate. And to measure overall performance, we use the commonly used area under the ROC curve, which computes the area under the curve traced out on a plot of false positive rates versus false negative rates as we change the threshold. A strategy that guesses randomly will have a curve that looks like the red dashed line and has an area under the ROC curve of 0.5, while a perfect classifier has a curve that looks like the dotted teal line and has an area under a curve of 1. So we compare Scod against several baselines, including using the Bayes deep neural network for uncertainty estimates directly. Other methods applicable to pre-train deep neural network models, like K-FAC Laplace and local ensembles. These are methods from available in the literature. And finally, deep ensembles, which is very commonly used approach, even though, as we will see in a second, not very applicable to the task we're considering here. So in these plots, we plot the classification performance on the y-axis, measured in terms of area under the ROC curve, as I mentioned before, and the total runtime to compute an anomaly signal for a single test input. So you want to push performance toward the left, upper left. You want to have area under the ROC curve as large as possible, ideally 1, and you want to have runtime that is as small as possible. We see that across a suite of regression and classification tasks, Scod in light blue outperform the baselines. And in addition, limiting the Scod analysis only to the last layer of the neural network, something referred to as a Scod LL, achieves comparable performance, but allows us to decrease further computation time. We see that in general, deep ensembles performs, at least for some tasks, quite well, but incurs much larger overhead computationally. So summing up, the key takeaway is that, yeah?
Sorry if I'm being slow. Can you help me understand the representational power of this? You're saying you're linearizing the network with respect to the weights. So
yeah.
This is different than if I did like an EKF through the network. But I can't quite get but you still said it's only going to give me a Gaussian on the output. If you could you just help me?
Yes, a posterior. So basically, you want to have a family of models. And so what we use as a family of models is a linearized network with respect to the weights. And so basically, we have delta W variation variables that are basically stem out of the linearization. For each fixed selection of the delta W variable, I will have a different neural network, meaning because I have a different weight assignment. The transformation of the input is still nonlinear. I'm not linearizing with respect to the input space. I'm only linearizing with respect to the weights. So actually, I'm reasoning about a continuous family of neural network models parameterized by these delta W variables. Now, the Gaussian is not with respect to the input. It is actually with respect to these delta W variables, for which I have a prior. Assume that these delta W are distributed.
You still get a Gaussian
Yes.
Linearization. So
exactly.
For any given input x, you get a Gaussian.
With respect to the weights, yes. Yes, exactly. You might ask, and that's a valid question, how general this model is. It still entails a nonlinear transform. So for each fixed W, I still have a nonlinear neural network. But admittedly, we're only considering models within the family of linear displacement from the baseline neural network. How general that is, we don't have a quantitative answer for that. Of course, is in a way a limited class, but at least from both quantitative and qualitative experiments we have carried out, it seems to perform quite well. Other opportunities to reason in terms of more expressive models? Absolutely, yes. Of course, the bottleneck is that you had to compute the posterior of your model. And the moment you break the linear formulation, then you run a little bit in the bottleneck. Of course, you can use particle-based methodologies and so on and so forth. But the problem is that we have, for runtime monitors, extremely stringent compute requirements. And you can also use other models like deep ensembles and so on. But this is so basically a bunch of algorithmic choices that try really to trade off compute time with representational power and what we can achieve. Now, there are a lot of open points, like, for example, I said I have a Gaussian prior. You can have a little bit more sophisticated priors and still do analytic posterior computation. How do you select the bandwidth of your prior? This for now is still on empirical. Yeah. Anyway, so in general, I mean, I propose one potential solution for runtime monitors. I think in general this is a very promising area of research. I would say that this is something that is still missing in the literature and also in products. So typically, when you have a safety critical system, you have a functional decomposition of your system, and then for each element, you would like to have a monitor. For some elements, you don't need sophisticated monitors. If you have a vehicle that is going at 300 miles per hour, you know that there is something weird happening with your tracking algorithm. But for some other aspects, you need these more nuanced monitors. And still, it's an open area for research. Of course, there is a lot of work from the machine learning community, but how to tailor all these results to the robotics use cases is still quite open. And in particular, in this context, we're working on a bunch of different things. For example, how to classify the nature of the severity of anomalies in order to better inform downstream decision making. So for example, if your network is perceiving a seagull as a peacock, probably from the point of view of a closed loop control doesn't make that big of a difference. So you don't want to raise an anomaly, even though maybe a peacock is out of distribution. We are working on statistical methods to Russ's point, more quantitatively quantify the reliability of a given monitors in terms of false positive and false negative detection rates. We are working on ways to provide a causal explanation to understand, okay, there is an anomaly, but what is really causing this anomaly? We're working on leveraging runtime monitoring for the purposes of data lifecycle management. That tends to be a huge problem in the community. So here the idea is to apply Scod to collect unfamiliar inputs that can then be used in order to retrain some of the neural network models. But you have to be very careful because you don't want to label everything as unfamiliar. Otherwise, the cost of retraining becomes very high. And finally, we're working on ways to optimize performance of runtime monitors in closed loop with a decision-making pipeline. So the point is, when you raise an anomaly signal, what do you do? Maybe you can switch your controller from a deep neural network dependent controller to a trusted safety policy. But how do you design this switch, and how often do you activate this switch is an open research question. Good. So now, an assumption that has been more or less implicit so far, and this is a little bit more the speculative side of the talk. So if you have ideas, I'll be excited to hear about your ideas. So as I said, the typical assumption that has been more or less implicit so far is that we have been assuming a given architecture for the Vstack, for example, in terms of its functional decomposition. And given this architecture, we have discussed different ways to improve performance, safety, and so on. A natural question is whether we can architect the autonomous system stack in new ways to improve performance and safety. Specifically, the classical architecture for autonomous robots, at least the one that is typically used in industry, is highly modular, where the key modules include detection, tracking, prediction, planning, and control. Even organizational companies are organized around these modules. Key advantages of these architectures include interpretability, reusability, and so on. However, as already mentioned when we were talking about the robustness of prediction algorithms to input uncertainty, these architectures introduce information bottlenecks, typically. It might give rise to integration challenges. So these different modules are developed more or less independently. You put them together, then it's very hard to make sure that everything works well. This has motivated in the past, I would say 5 years or so, to work on end-to-end architectures, which directly link perception to control in the simplest possible form, even though by now there are more sophisticated ways, through a neural network, and only implicitly encode key capabilities such as, for example, agent prediction. As key advantages, an end-to-end architecture, one could argue, can achieve a level of performance of optimality that is unachievable by modular architectures, and also might require less hard work in terms of tuning the different components of a modular architecture. However, among other things, it's very difficult to make any sort of safety claim about these end-to-end architectures. Now, I've said that end-to-end architectures can achieve a level of performance and optimality that is unachievable by modular architectures. But is this really true? And it turns out that the notion that a modular design is necessarily suboptimal is indeed not correct. And to make this point clear, I'm going to consider a very simple Markov decision process setting. So specifically, let's consider a system we want to control with the state X, and we want to control it by selecting control actions U, based on measurements that are possibly noise corrupted, which I denote with Z. And then find the information vector as the history of measurements and controls up to the current time, I is OK. And we consider the general class of policies that map information vectors into control actions. The problem is to find an optimal policies that optimizes average performance according to a given cost structure represented by the functions G sub K's, subject to the system dynamics represented by the functions f of k. Now, one can show that the conditional state distribution represented as capital P is a sufficient statistic. And an optimal controller can always be written as a mapping from the conditional state distribution to control actions. This is from one of the many books from Bertsikas, chapter 5, volume 1. Explicitly, these results provide a decomposition of the optimal controller into two parts. An estimator, which uses the current measurement and the previous control value to update the distribution P, and then an actuator, which generates a control input as a function of the distribution P. And this interpretation has formed the basis for various suboptimal control schemes that separate the controller a priori into an estimator and an actuator, and attempt to design each part in a manner that seems reasonable. But importantly, the suboptimality of these schemes stem from the suboptimal design of the individual components and not by the modular structure per se. And the reason why there is suboptimality in the design of components is that oftentimes key couplings between the different components are not taken into account. Now, these results might be obvious to some, less obvious to somebody else, but the key point is that modular designs per se, they're not necessarily suboptimal. So given this insight, the natural question is whether we can get the best of both worlds in terms of architecture designs. For me, modular, as we do today in production, and end-to-end, which is like the more academically emerging way of doing things, are two ends of the spectrum, and there are a lot of opportunities in between. Specifically, I'm working on modular architectures, or novel architectures that are still modular, but better align and integrate the different modules in the autonomy stack. And in particular, I'm looking at more expressive and learned representations of information flows at multiple levels of the Vstack, metrics that capture upstream and downstream couplings between different modules in the autonomy stack, for example, would planning-aware prediction metrics lead to better prediction algorithm? By planning-aware, I mean metrics for prediction and trajectory forecasting that quantify to what extent an error in prediction might lead to a plan that could be unsafe because of a potential collision. And third, algorithmic tools to co-design the different modules by leveraging the coupling metrics and the learned representations. So since we're running a little bit late, I will skip the work on learned representation and metrics, and I will talk instead on how we can have differentiable yet modular autonomy stacks. So to enable this concept, we are developing a neural programming framework to present existing modules as a differentiable computation graphs, thereby keeping the modular structure, but allowing gradient-based learning to improve upstream modules for a downstream task. And let me make this idea a little bit more concrete by going back to the task of prediction and planning. So in modular architecture, you have many different models. We're just going to focus on two models, prediction and planning. And I'm going to discuss how we can co-design the two by leveraging the neural programming framework that I just mentioned. Specifically, consider deep prediction models, such as a Trajectron++, which consumes as inputs past tracklets, that is a sequence of waypoints, for all traffic agents on the road, and outputs predictions about the future trajectories of such agents. And this prediction model, for example, could be Trajectron++. And these predictions are then fed into a planner, in our case, a model predictive controller, which optimizes a handcrafted cost function to compute control actions for the autonomous vehicle. So in a conventional model architecture, the prediction model is trained from driving data, while the planner is handcrafted. You select some design parameter for your NPC, but then there is no data-driven component. So in our differentiable architecture, we replace the planning algorithm with a differentiable planning algorithm, specifically a differentiable model predictive controller from prior work, not in my group. What this allows us to do is to use data at the end of the pipeline, but propagate losses through the planner and improve the prediction model so that, for example, it focuses on making predictions that are critical for planning. So this project is still in an early stage, but in preliminary experiment, we have seen substantial gains that stem from co-designing the two models, prediction and planning. In particular, we have considered the setting where the data set is new scenes, and the planner outputs a control sequence over the next 3-second horizon. The prediction loss is negative log likelihood, and the end-to-end planning loss is a mean square error with respect to expert trajectories in the data set. The result is that if we increase the weight of the planning cost compared to the weight of the prediction cost, then the prediction model starts to free up its representation capacity to focus on predictions that are focus more on predictions that are indeed safety critical, thereby improving end-to-end performance. Of course, you can use this concept in many different ways. As a byproduct, we are using this formulation to tune in a data-driven way, among other things, the parameters of a planner's cost function. And in particular, the weights, θ1, θ2, θ3, and so on, of a cost function. This is a notoriously difficult task to do at hand, also because it's very much scene-dependent, context-dependent. So there is not like only one set of theta values that work well throughout all the operational design domains of a vehicle. And we're working on using this approach to train the cost-weight parameters in the NVIDIA Vstack. So I think this way of thinking has a lot of potential because it allows us to retain modularity. We like it because of its reusability, because we can, I mean, if I see an NPC, I know what the NPC is doing. But at the same time, I can use data to train the system as a whole. So summing up, key takeaway message here is that there is a full spectrum of architectural opportunities between end-to-end architectures and modular architectures. And we're just scratching the surface in terms of what these opportunities are. And the many different ways you can instantiate this gray area is in terms of defining better representation for how information flows with respect to the components, task-aware evaluation metrics, and of course, differentiable algorithms to co-design the modules. So I will close it here. I hope that I gave you a good overview of my work. I would like to thank all the collaborators I have the privilege to work with, in particular the students in the Autonomous Systems Lab and the researchers in my research group at NVIDIA, the Autonomous Vehicle Research Group, and of course, David here from MIT. And should you have any questions, please let me know. And if you don't have a question now, but it pops up later, feel free to shoot me an email. Thank you.
Thank you for the great talk. I've got the mic. So anybody have any questions? All right, farthest possible person.
Thanks for the great talk. So I have a question regarding like differentiable planner. So for example, if you make the planner differentiable, I imagine there are cases where the gradients will blow up or just go to zero. Like, how do you tackle that problem?
Yeah, so the moment you make some of these models differentiable, you have usual issues with differentiable models where you use gradient-based learning. So you can have vanishing gradients, you might have overfitting, and there is no silver bullet here. So there are a number of techniques developed in the machine learning community that we are considering. But as I said, this is still in fairly early stages. But it's a good point. There is no free lunch.
OK, thanks.
Other questions? Eric.
So before you mentioned you had the theta variables for weighting the loss for doing backprop to the planner and the predictions. And you mentioned that if you tuned it a certain way, it would give you better safety guarantees or safety assurances. Can you describe, do you have like a concrete example of what that would give you? Or
well, not safety guarantees. Basically, if you, so you have a weight on how much you train about, care about the prediction accuracy and how much you care about planning performance. Now, prediction accuracy is agnostic to how a forecasted trajectory might affect planning. So maybe you have an agent that is very, very far away, dynamically speaking. So it's very far away, and you're really trying hard to forecast the trajectory for that agent. But in reality, it doesn't really matter that you really nail the trajectory of that agent because its effect is going to be inconsequential. The problem is that if you weight all predictions equally, you might actually try to do very hard work to really nail that forecast while giving up some of the accuracy for vehicles that are nearby again, dynamically. And so the question is that if you use this notion of planning awareness, you can try to put more weight, which is a pretty intuitive idea, more weight on things that matter the most so that your model really learns in focusing your attention on what really matters the most. So that's basically the underlying idea.
Awesome, thank you.
That said, there is no particular safety assurance or guarantee that arises from that. The safety assurance, one safety assurance is that since we're still dealing with fairly carefully designed MPC control algorithm, we still have the notion of constraints. So that's one way of having at least a bit more trust that the algorithm is going to do something sensible.
I'll ask a question. So as you've now spent time at NVIDIA,
yeah.
Has that changed your view of assurance cases in any dramatic way? Like, has it made you think differently about the type of work you've been doing at Stanford only?
Yeah, that's a great question. So what has changed a little bit is, more than change, I would say augmented, is first a notion of safety KPI. So basically measures to see whether what you have architected works well enough, which I never thought about the importance and difficulty of it, but actually is essential. One, in terms of external facing activities, so basically you're working with regulators or other automotive companies, and you want to show that your system is safe, but also internally, so when the perception model is good enough. And there are a lot of interesting aspects that are still open, surprisingly open. Like, for example, you want to see whether a given perception network is, or perception module is good enough. And so what you would do is, OK, I have a test set. I have a number of agents, and I see that I can detect all agents in the scene. But in reality, you don't really care about detecting perfectly something that is very far away from where you are. Again, far away means dynamically speaking. So basically, these promoted some research on how to use techniques, for example, from reachability theory to weight the different errors that you do in terms of what could be the potential consequences in planning. So that is one. The second one is that in the automotive sector, there is something referred to as ASIL decomposition. And so basically, you decompose your software stack in all its functionalities, and then you attach safety requirements to each one of them. The strictest requirement is referred to ASIL-D, that right now is almost impossible to achieve with a deep neural network. And so that the fact that you have a requirement really changes the way of how you architect the autonomy stack, for example, in terms of algorithmic pipelines. So I never paid attention to it, but that gives rise to a number of interesting questions, like, for example, how algorithmic pipelines do coexist, and how you can actually decompose a high-level, a very strict safety requirement into less strict safety requirements by having independent algorithmic pipelines. So that is, I would say, a second one. And then there is all the aspect of runtime monitors that I was already aware of, but really got a better appreciation when working with the automotive companies and with NVIDIA. So that is all great. The thing that I was a little bit surprised is that to some extent, without going too much into the details, but I was hoping that simulation was by now a more mainstream tool to really, for developing for sure, but really to get assurances about your design. And we are still quite far from that. Ideally, you have a new design, and you can do most of the validation in closed loop simulation, and still there are fundamental research gaps there. I think photorealism, we're quite good at it. That is, for example, with DriveSim at NVIDIA. But behavioral modeling and reasoning about closed loop interactions in all the possible nuanced ways a human can interact with the NAV, we are still very far from that. And there is a push to go toward that. For example, Motional has released a new plan, but still quite simplistic. Awesome. Yeah, sorry for the long answer.
Thank you very much. And a great way to close the session. So thanks
very
much. Yeah.
Thank you very much.